This statement is false. If it is true, then it is false. If it is false, then it is true. This is known as the liar's paradox, and has been quite vexing for many people over the years. Many people have asked whether the statement is true, if it is false, if it is both, if it is neither, if it's something else, or even if it makes sense to say it at all. Now, I may not be a philosopher capable of answering these questions, but I do know a bunch about math, and in particular, I know there is a result known as Tarski's truth theorem, which addresses whether or not the statement can be expressed in logic itself. In order to address Tarski's truth theorem, though, I want to take us across a rabbit hole. First, a formal logic, where we see how math is structured and abstract that to the point where logic can look in on itself. Then, we'll look a little bit at model theory. It will tell us a few things that we will need to prove Gödel's first incompleteness theorem. It may not be directly related to Tarski's truth theorem, but it is close enough, and all the same materials are needed to prove both. If you are familiar with any of these topics, you can skip the sections. The time codes are in the description, if I remember to put them there. Since the largest part of this video is concerned with Gödel's first incompleteness theorem, I thought we should look at its statement. Any recursively enumerable theory in a countable language capable of modeling Robinson arithmetic is either inconsistent or incomplete. This is absolutely overkill for our purposes, especially for Tarski's truth theorem. The material needed to prove this would be incredibly overkill. So, what we are going to do instead is we'll look at a more historically accurate version, closer to what Gödel initially published, namely, piano arithmetic is incomplete. Piano arithmetic being the common way to describe arithmetic as we do it, with plus, multiplication, and it defines the natural numbers as starting at 0. What Gödel's first incompleteness theorem says is that these rules are not enough to say every true thing there is about the natural numbers, i.e., there are truths that cannot be proven. We'll be following the version of the proof found in the book on screen now, Gödel's Theorems and Zermelo's Axioms, a very thorough book that I enjoyed, but some might find somewhat dry. It is extremely in-depth and goes into a lot of interesting details I was not expecting to see. Since we want to find a rigid language for math, in order to formalize it, we might want to look at an informal example first. For that, I have chosen the proof that I want to show, honestly, and it is Euclid's theorem on primes. Namely, there are infinitely many of them. Historically, Euclid was not a fan of infinity, and logic finds infinity rather hard to deal with, so we are going to rephrase it closer to the historical example. For any number n, there is a prime p larger than n. And like with many other proofs, I am now simply going to assume another result. Any number m has a prime factor. And again, it might help to rephrase that one somewhat. For any number m, there exists a number p, such that p is prime and p divides m. Armed with these, we can now move on towards a proof. On the left hand, I'll keep our goal, Euclid's theorem, and our preliminary result, the existence of prime factors, visible. The first part of our proof is to simply take an arbitrary number n. Then we define, using this n, a new number m as n factorial plus 1. N factorial means we take 1, multiply by 2, multiply that by 3, and so on until we reach n. Now, we may note that any number between 2 and n, which we'll call x, cannot divide m. For example, we could try doing long division on m, and note that for any of those, we will have a rest of 1. Now, by our lemma, we can take a prime factor, p of m. Since p is prime, p cannot be equal to 1. For a more in-depth discussion of this, in the description you'll find a video by another proof which discusses why we choose p, in this case any prime, to not be 1. Since p divides m, by our note earlier, it cannot be any number between 2 and n. Since it now cannot be 1, 2, or any other number up to n, it must be greater or equal to n. So p is now both prime and greater than n. Since n was arbitrary, we could repeat this for any number, and it holds for all possible n. Now if you look at the time code and notice that this video isn't 20,000 hours long, you can guess that we aren't going to fully formalize this proof. We are simply going to look at the elements of it that we can use. For example, we have a domain, namely the numbers in this case. This is where our variables, our constants, and so on live, where functions take inputs and give outputs. Speaking of constants, we have several constants in our proof. Here we use 1 and 2. We also have a lot of variables, n, m, x, p. These are stand-ins for other objects in our domain. These could be constants or stuff we construct out of constants. Functions also make an appearance here. Addition, multiplication is hidden in the factorial, and the factorial itself is also a function. We also have relationships that relate different numbers. Equality, inequality, greater or equals, strictly greater, and so on. We also have logical operators such as the not, the negation of stuff. For example, here we have the negation of equality. We also can connect statements with and. And we also have quantifiers where we quantify what space in our domain that our variables could live in. Here we say for all n, it is true. Now, these elements of logic aren't quite a complete list. We have or that connects two statements, and we look at the inclusive or, that is true as long as one of the two statements is true. This is where we get to all those fantastic answers online where you ask a question of or and they simply reply with yes. We also have the quantifier of existence. There exists. This is if we want something to hold for at least one variable. Now, beyond these building blocks of statements, we also have some statements that we assume to be true. We call these axioms. And in order to create new ones from axioms, we have rules of deduction, such as modus ponens, which takes the statements phi, and a statement phi implies psi, and says that if we have both of these, we also have psi, aka I am a human, all humans are mortal, therefore I am mortal, to take an example from Socrates. We also have generalization. If we have a statement and some variable that could be anything, we simply slap a for all of that variable in front of it. This is what we did in the last step of our proof, where we said this holds for all n. Now, if we look at an example of one of our statements, for example, the lemma that we had, for any number m, there exists a number p, such that p is prime and p divides m, we could translate this into formal logic, into these symbols that we defined earlier, and with those we get this monstrosity, which is absolutely hideous and quite difficult to read. It is usually rather excessive to express things like this, but with some practice you can get better at reading them. To that purpose, there is another video from another roof that is linked in the description that deals specifically with how to read such statements, and it is quite useful. The reason we formalize stuff like this, aside from these kinds of proof, is that they tend to be easier to program in this form than it is in natural language. This allows for stuff like the brute force computation used at the end of the four-color theorem, or for proof-assistant-based programs such as the Xena project that wants to verify modern mathematics, to make sure that we never skipped a step in between. Instead of going through a large example, I'll simply list how we build up these formulas. At the center of these, because they tend to be very nested, the smallest part of this matryoshka doll of random symbols are terms. These are constructed either out of constants or variables, and we can take terms that we have already constructed and plug them into functions, such as x times y or x times x plus y plus 0. These are all further examples of functions, and they can become quite fascinatingly complex. Now, moving on, you get formula, because terms alone aren't interesting, it's just a thing. Formulas start relating them, either by checking whether two terms are equal or plugging into other relations we have. N is less than or equal to n plus 1, or x is greater than x plus 1, are both examples of formula. Now, once we have formula, we can start manipulating them with the logical operators we had before. We can construct ones using not, which flips the truth values that we would hope to get. We can connect to saying and it is true in the case that both are true and false any other time. We also have or, where it is true as long as one of them is true, and only false if both are false. We also have quantifiers, namely for all x, phi, which we saw earlier, and there exists x, phi. Since variables play such a profound role in both mathematics and in these formula themselves, we are going to define a few terms to describe their roles. They are bound if they only appear after quantifiers, such as here. The only occurrences of v are after the for all v. Otherwise, we call them free, and if we give our formula a name, we typically write the free variables in brackets, such as here, where we do not have a quantifier binding v. Now, if a formula has no free variables, it is called a sentence, which I honestly think is just neat. That's it. It's just neat. Now, after our formula, we stated that there are axioms, these statements that we hold to be true no matter what. Now, since we're talking about formula and not statements, we need to list them. There are many ways of listing the logical axioms, and all of them are overly complicated and confusing. Here are a few examples. We have the first one that represents the law of excluded middle. L14 is a law of identity, and in between, I will let you try and decipher what exactly these two mean. Note that phi and psi are any formula that we can construct. For those interested, I will briefly show the whole list of axioms for this specific case of formal logic. Beyond the logical axioms, we have specific axioms that we care about in this case. Here, we care about the piano axioms, since we want to talk about the natural numbers. We have this language, expressed by this fancy L, which contains the constant 0, the function s, which is called the successor function. It gives us, in essence, the next number. We have plus, and we have multiplication. The first axiom, p0, tells us there is no number that comes before 0. The next axiom tells us how the successor interacts with equality. In this case, it tells us that the successor function is injective. There are no two numbers that share the same successor. Then we get how 0 interacts with addition, followed by how the successor interacts with addition. Then we have how 0 interacts with multiplication, followed by how the successor interacts with multiplication. And finally, we have a whole lot of axioms at once. Phi here is a function, a formula with a free variable, and P6 says that we can do induction on this formula. Now, with all this out of the way, we can finally move on to describing how formal proofs work in mathematics. A formal proof of a statement, psi, in a theory, which is just our axioms, is a sequence of other formula, phi 0 to phi n, where the final formula, phi n, is the same as our formula we want to prove, psi. And for any of these formula, we have one of the following cases occurring. Either it is an axiom, could be a logical one, could be one of the ones we are assuming, or there are two previous formula, in the sequence, such that phi I is obtained by modus ponens from the other two, or there is only one previous one and a variable such that phi I is achieved through generalization. If these steps are obeyed, we have a valid proof, a formal proof of psi. And in this case, we write T with this weird symbol that I will simply read as proves in the future, but it looks nicer and more formal and all that if I write it like that. To finish off this section, there are a few terms I want to define. First off, whether a theory is consistent or not. It is inconsistent if we can prove, for some statement, psi and not psi. Notably, this is a contradiction. If you've ever done a proof by contradiction, this will seem familiar. If you know of the principle of explosion, you will know that from this we can prove anything we want. Absolutely anything. However, if we cannot prove this for any psi, then we call T consistent. Secondly, we call T complete if for any formula, either T proves it or T proves its negation. As I mentioned earlier, an inconsistent theory can prove everything, but consistent theories don't necessarily have the property that they can prove every formula. In that case, we call T incomplete, and by the end of Gödel's theorem, we will show that piano arithmetic is such an incomplete theory. Now, there are two main difficulties that Gödel's proof faces. The first being, how do we translate these formal symbols, these formula, these axioms, these rules of deduction into piano arithmetic? How can we encode what we are trying to say? The second problem is that almost all of our stuff, from the terms to the formula to proofs, are defined via sequences of stuff. And all we have at our disposal is the successor, addition, and multiplication. So we need to find a way to define sequences. And while I'll skip over the technical details, Gödel found a way to describe both of these problems rather ingeniously. The Gödel numbering, aka how Gödel solved the encoding, takes all our symbols, here 0, s, addition, multiplication, equality, negation, and, or, implication, for all there exists and are variables, which, for simplicity's sake, we restrict ourselves only to variables of the form Vn, and he assigns to each of them a number. I will be using the absolute value of our symbol to signify its Gödel number. Note also that all the numbers can be represented as simply strings of s in front of 0. We apply the successor function one time to get 1, twice to get 2, 3 times to get 3, and so on. So when I write down the number 12, that's actually s of 0. And that's too tedious to write, so I write down 12. To decompose the formula we have earlier, we note that they are nested like Matryoshka dolls. And each step we have a operator, be it a formula acting on terms, an operator acting on logical symbols, or a quantifier acting on a variable and a formula. With these, we always have one or two inputs. So we can then define the Gödel numbering of the statement as 2 to the power of whatever operation we're doing times 3 to the power of the first input times 5 to the power of the second input. Now, since prime factorization is a thing, these are all going to be unique. And we will see that we can also define the power function using only addition and multiplication. So all of this can be done entirely in piano arithmetic without needing to appeal to what we learned in grade school or high school, or on brilliant.org or Khan Academy or wherever you learn math. It's been too long. I have forgotten too many numbers. I have not seen 20 in quite some time. We will start with an example. We will take 2 equals 1 plus 1. Quite a simple sounding statement, and we will find its Gödel number. The first thing we want to do is to transfer it entirely into the symbols that we are using. It means S's, zeros, no 2's, no 1's. Now the outermost operation is this equality. So we have 2 to the power of whatever equals is, 3 to the power of our first component, which is the 2, and 5 to the power of what is the 1 plus 1. We then need to further break these down. For the power of 3, we have the outermost operation being S. For the power of 5, the outermost operation is plus. So we get 3 to the power of 2 to the power of S times 3 to the power of S0. And similar for 5. We now simply need to break down these S0s, these 1's, which turn into 2 to the power of S times 3 to the power of 0. Now with all of these ready, we can now move on to replace the symbols with their Gödel numbers, which gives us this lovely mess. This turns out to have over 500,000 digits, so I will not write it out here. I did not bother writing a script to write out the full thing, and Wolfram Alpha gives up after a while. Now, not all numbers represent formula. Not even most numbers represent formula, so we need to find sequences so we can test whether or not a given number represents what we want it to represent. For that, Gödel constructed some very neat formula and functions in piano arithmetic. It's ingenious, but extremely dry, extremely technical, and I'm still not sure if I get all the details. So I'll simply present the end result. We have a formula sequence of S that tells us whether or not S encodes a sequence. If it encodes a sequence, it is the unique number encoding that one. Finally, A also defines LH of S, which is 0 if S is not a sequence, and it is the length of the sequence encoded by S if it is a sequence. And you might notice here, this means we are only talking about finite sequences. And we say that S encodes a sequence S sub 0, and so on until S sub LHS minus 1. It's sometimes more useful to start sequences with 1, but since we've started every numbered list with 0 instead of 1, we are sticking to that. Damn this minus 1. Also of note is that any finite sequence that we can think of can be encoded to some S. To see this sequence in use, I thought it might be useful to look at the definition of the power function. So we have inputs x and k, and we want to define what y is. So first, we say that there exists some sequence, because we want to define exponentiation as repeated multiplication. We want the length of the sequence to be k plus 1. That means S of k. We also want the sequence to start with 1. And we want every element of the sequence to be created by the previous one by multiplying by 1. And finally, the last element in this sequence should be our y. That means t is a sequence that encodes 1. Then we multiply that by x, so we get x. We multiply that by x, giving us x squared, and so on until we get x to the power of k. Now, this trick is fantastic, and it allows us to define again and again these repeated actions. That means we could now also define the factorial. If you really had no time, you could also define the arrow notation and many more. However, all we need for now is the exponent. Next, we are going to look at the example of trying to recognize a term. So, as we said, most numbers do not encode for a term, let alone a formula. So, we have first our variables. Recognizing variables is easy, since we only assume they have the form v sub n. It means if there is an n, such that our number is 2n plus 1, then we are encoding a variable. Next, we say that C codes for a term t, first off, if C is a sequence, if its last element is t, and if every previous element is either a variable, 0, which is our only constant, or we have two previous ones, such that C is the successor of one of them, is the addition of both, or the multiplication of both. This means that C is constructed stepwise by variables, constants, or previous terms plugged into functions that we have, which is exactly how we defined terms earlier. Formula would be the next step, and that I will leave as an exercise to the watcher, because it's a bit longer and has a few more cases. Finally, we say T encodes a term if there is a C coding the construction of T. If we want to recognize more, we have the formula, which, as I said, I'll leave as an exercise to the watcher. And we have the following: MP, which takes 3 inputs, checks that 2 of them are actually formula, and that the third one is the implication between them. This might be noted that these are the conditions we require of modus ponens, which is why we chose the abbreviation MP. It tells us if F was constructed from the other two, and they have the shape of modus ponens. Next up, we have generalization, for which we check that we have a variable, a formula, and that our new formula that we are checking has the shape of the generalization of the previous one. This, again, tells us that it was constructed using the rule of generalization. In order to recognize axioms, we encode them similarly. We say that F is an instance of the axiom L1 if and only if there are 2 other axioms that are both formula, and that F has the shape of our first axiom. F prime implies F prime prime implies F prime. This is an axiom, an instance of our axiom phi implies psi implies phi. Now, if you don't think this axiom is logical, or if you think it's a tautology, it sadly turns out that we need it as an axiom. So we test for it. And we can test for all of them, which, if you feel so inclined, I encourage you to come up with the structure for yourself. We can encode all of these together into a single axiom, a single formula, by simply slapping a bunch of ors between them. And this tells us if a F encodes any axiom that we want. We can also include the piano axioms in there. Now we can move on to recognizing proofs. We say that C codes a proof of F if C is a sequence, and the last element of the sequence is f. And any element of the sequence is either an axiom or is constructed by modus ponens using two previous ones, or is constructed by generalization with some variable, or nothing else. That simply is the whole structure of how formal proofs work, and it tells us if C encodes a proof of F. Now we can also say that provability of F is a statement there exists a C encoding a proof of F. This tells us if the statement, the formula encoded by F, is provable. And with this, we have now managed to get formal logic and the piano axioms to look at themselves. We have encoded provability within simply the rules of numbers, something which, quite frankly, is weird and has confused many people, including the people who most were looking for something like this, such as Hilbert back in the early 20th century. Now, there's a final thing we need from formal logic, namely the diagonalization lemma. This comes very close to becoming a category theory topic, and quite frankly, this video is long enough, so I will keep it brief. The lemma states simply, or less simply, if we have a formula with a single free variable, then we can construct a formula with no free variables, i.e. a sentence, sigma psi phi, such that sigma phi is equivalent in piano arithmetic to plugging in its Gödel number into phi. This meshing of a function with itself is why it's called diagonalization. We'll see a bit more, maybe, in some future video, why it's called that. For now, in the description, I'll have linked a video on diagonal arguments in general, and if you want to, you can try connecting the proof of the incompleteness theorem with that, if you want to. For model theory, I want to keep this rather brief. A few of the main distinctions is that in formal logic, we look at formula with little to no meaning, and in model theory, we look at statements where the meaning is there in the structures that it is talking about. In formal logic, unlike model theory, we simply have grammar and rules of deduction. Model theory has actual structures where stuff means stuff. And finally, this is a rather big distinction, so it bears repeating. On the formal logic end, all these symbols do not have inherent meaning. Hilbert once said that geometry should still work if you replace all the instances of line, point, and plane with beer bench, butt, and beer. But in model theory, once we assign the things to objects, stuff becomes true or false. There is no real in-between in the real world. Either this video is long or it is short. Now, with the talks of objects, we need to talk about a model for our theory. Here we have the standard model of the natural numbers, represented by the blackboard bold N, not to be confused with the website formerly known as Twitter. The structure of this object is that we have strings, the first string being simply the number 0, and then we successively add more s's in front of it. So we have 0, s of 0, ss of 0, sss of 0, and so on. We continuously add more, and any finite string of s's in front of a 0 is an element of n. You might be used to picturing this as 0, 1, 2, 3, but this turns out to be a bit more useful for formal logic and model theory. Now, we can define addition in these. In that case, we simply concatenate the s's and put them in front of a 0. And for multiplication, we simply replace each s in one of the strings with the entire string of s's from the previous one. Now this is what we would call an interpretation of the piano axioms into n. And we write that n models, that's what this weird symbol means, phi, if phi becomes true with this interpretation. And because we take the piano axioms to abstract the properties of the standard model, we have that phi models the entirety of the piano axioms. Now there are a few important results that I want from model theory. First off is the soundness theorem. If M models a theory, and the theory proves a statement, then M models that statement. This tells us that the whole thing with formal logic, where we abstract away from the truth, isn't completely meaningless. We can still bring it back to models and truth. What we can prove is still true for stuff that matches our assumptions. In our particular case, this means that since n models PA, if PA models some formula phi, then n models phi. Since we know that one of these two statements is true, we can drop it. If PA proves phi, then n models phi. A second important result is that if our standard model proves that a number encodes a proof of some statement, then it encodes some proof of a statement. Seems tautological, but there actually is a proof for this. And if it encodes a proof, then we can literally write down that proof. So the piano arithmetic must also prove our statement. Conversely, if we know there is a formal proof, then we can encode that proof into some number. And if there is some number, then we can plug that into C subscript proof, and it is true, so n must model that. So to combine these two, we have that the piano arithmetic proves a statement if and only if the natural numbers model our statement prove of it. Next up, a small note. For any formula, n either models it or n models its negation. Unlike theories where you can be incomplete, models always model stuff or its negation. It is either true or not. This was noted by Aristotle when he formalized the law of excluded middle. For theories, however, this isn't necessarily the case. It could occur that a theorem is not provable, neither is it its negation. The statement that we will see later is one such statement. And lastly, there is a certain property of the natural numbers. If we have a formula with a bunch of free variables and a whole bunch of numbers to plug in there and n models them, then PA proves the formula with those numbers plugged in. This is notable since this very rarely occurs with other models, even for the piano arithmetic. This usually is a one-way street that proving something implies modeling. And notably, all the functions that we defined earlier, all these formulas such as prove, are such ones, because if you try programming them, you can prove that these will eventually end. We will either get a result of, yes, there is a proof, or no, there isn't a proof with these axioms. So it is very interesting to see. With that, we can move on to the proof itself. On the left hand, as usual, there are the statements that we will need, and on the right, I've already started by defining a new statement. We have phi of v0. It simply means not our provability predicate of v0. Now we can use our diagonalization lemma on this, since it has a single free variable. It means we get a sigma that is equivalent to plugging in its own Gödel number into phi, which means that is equivalent to not provable Gödel number of sigma. This may look confusing, but it is rather useful. We now split ourselves into two cases. The first one where piano arithmetic proves sigma. If that were the case, we can encode the proof into some number c. Then, since that is a natural number, we can then find that PA proves that C encodes the Gödel number of sigma. But if it does that, then it proves that there exists such a C, which means that PA shows that sigma, its Gödel number, is provable, which is contrary to our premise. Since PA proves sigma, that means PA proves not provable Gödel number of sigma. So these last two lines give us a contradiction. That means case 1 cannot occur, which leaves us with case 2. We start by rephrasing what not sigma means. Not sigma is not provability of Gödel number of sigma. Double negations cancel out, so we get PA proves Gödel number of sigma is provable. This means, by the soundness theorem, that n must model the provability of sigma. This means that, as we saw earlier, since n implies models the provability of sigma, PA must prove sigma, but this contradicts our assumption, which gives us yet again a contradiction. So we had the case where PA proves sigma, leading to a contradiction, and the case where PA proves not sigma, leading to a contradiction. Since it cannot do either of these, PA must be incomplete, which was what we wanted to prove. The sentence sigma itself is sometimes called the Gödel sentence, the unprovable sentence, and we may note that in our second case, n proves not sigma, n models not sigma, since provability of the Gödel number of sigma is its negation. Since that is what led us to the contradiction, we can know in this meta-mathematical way, from us looking in from the outside, that n must model sigma. So sigma is the unprovable true statement that was mentioned earlier. This statement is false. This is the whole thing that started the discussion. We wanted to find out whether or not this was mathematical. And we know that piano arithmetic and logic together can look back in on themselves. So why not hope that they could look into the natural numbers, jump out of their own confines, and look at something where truth is defined. And to that goal, we would want a statement truth to be such that if n models a statement, if psi, phi in this case, is true, then n models truth of its Gödel number. This is the property that we would want truth to have, because we cannot define truth on a purely formal level. We need the natural numbers where these abstract formula become meaningful statements. Now, Tarski's truth theorem, however, says that this formula cannot exist, which, depending on how you look at it, is either very sad or absolutely fascinating. We shall now look at the proof, and like before, we are going to assume something to start. We'll assume that such a formula can exist. On the left, we have our definition and the diagonalization lemma, the only two properties needed right now to prove the theorem. So first, we use a diagonalization lemma. Since truth has a single free variable, we again get this very confusing looking sigma that is equivalent to not truth of its Gödel number. Then we can assume again, if n models truth of sigma, truth of its Gödel number, then by the definition, and must model sigma itself, because that's a property we hope truth to have. But by the definition of sigma, this implies, this is even equivalent to the fact that n models not truth of the Gödel number of sigma. This first and last line that are equivalent to each other contradict each other. Since n is a model, it cannot be inconsistent. Only one of the two can occur. So we have achieved a contradiction. And thus, our first assumption that truth exists is incorrect. Now, if we look at what sigma means, sigma says it is not I am true, aka I am lying, aka this statement is false. So, sigma itself, if it existed, would be the liar's paradox. However, it would directly mean reality of the natural numbers is contradictory. So it cannot exist. It is not mathematical, which may be unsatisfying to some, but good enough for me. Thank you for watching. I hope you've learned something. This is my first video, so I expect it to be very scuffed.